Just 1 second. Okay, guys, this is the note that I just uploaded through my course views from last week. And what we discussed from last week, we just mentioned about what the formulation we use. The basic formulation we apply on is a force, which is the force at the degree of freedom. This is the vector force. And corresponding to the force at the degree of freedom, you have the displacement. And what you do, you know that the dimension of the force has to be the same as the dimension of the displacement. So that's why when we're looking at the metric algebra, the linear property of the metric algebra, we know indeed that to make this one compatible, you need to have the size or the dimension of the K matrix, which is the global stiffness matrix, to be symmetry. So it should contain the row, the number of row to be similar to the number of column. So that's why you have the symmetric K matrix. And the K matrix normally it can tell a lot of things. It's not only to be used to take the inverse of the K to the force, and then you got the displacement. Typically, K matrix can tell the performance of your discretization and also the performance of your model, right? If you can have if the K matrix can be invertible, if you can have an invertible matrix, which is of course this is it has to be symmetry matrix, right? Always you always have a symmetry. So the matrix or the structure that you're looking at is mean this is stable, right? So you have the good structure models, so it can be invert, right? So inversible. When we talk about the inverse matrix, we're saying that this one we call them as a non-singular matrix. By looking at the mathematics, right, rules, we say that to make it solvable, you need to have the matrix to be non-singular matrix or inversible matrix. And of course, this one is had to be symmetric, right? Because of the equation that we use, if you just refer back to form the K matrix, we use this standard equation, right? And the standard equation that we have, it is the double integration. This is over the volumes, right? You have the thickness, dx and dy, and you got the transformation matrix. This is derived from the derivative of your shape function time with the hook matrix, which is depend on whether you're looking at the three-dimensional space or the simplified model into the in-plane, which is either the in-plane strain or the plane stress. So you have the E, which is the stiffness matrix. This is the local stiffness matrix to be 3 by 3, right? According to how you model the structures. And the length of this is depend on, okay, let me talk first. To satisfy this rule, we use the green function. You learned that already. But in the following to what we derive it and how we use the isoparametric properties or the isoparametric four-node or the bilinear models, we want to transform the actual coordinate to be what is called as a natural coordinate, which is in terms of the eta and the curses and the eta terms. And to transform the actual coordinate to be the natural coordinate, we need the information on the Jacobian matrix. If you refer to what you learn in the mathematics, you want to convert from one coordinate system to be the another coordinate systems, we need the transformation matrix, and this transformation matrix we call as a Jacobian. And we get the Jacobians, and what we do, we take the inverse of the Jacobian, right? So that's why we have to transform the derivative of the shape function to be the B matrix in terms of the natural coordinate. And this is the way how we derive them. So I just put all the jigsaws, right, that complete all the information that we have here. So basically, we define the strain at the first derivative of the shape function. This is the derivative form, right? The strain in X, the strain in Y, the shear strain, and this is the derivative of the displacement in X and Y. And we define the displacement in terms of the shape function. Then you derive them by taking the derivative of this. And then you can expand the forms. When we expand the forms here, of course, this one is just about how you can match them to the derivative of X and Y and so on. This is in terms of the strain in X, strain in Y, and the shear strain. The green in the matrix, this one is the inverse of the Jacobian matrix. So that's why we take as a tau, right? Which is the Greek symbol. And the length of them is about how you take the first derivative of the shape function. This is written in terms of the natural coordinates, right? So we want to transform two of the coordinate systems, so we have to use this. On the other hand, if you don't want to transform them, you want to use just a standard quadratic, the quadratic element. So you derive everything in terms of the real coordinate x, y. So you don't need to use this, right? But what I discussed before, there are so many benefits of using the natural coordinate, and this has been popularly used in the finite element models, especially for the 4-node bilinears. And this one I define them. So how we derive them, this is coming from the Jacobian matrix. And if you don't know, if you forget what the Jacobian has been used, this is the way how we derive them. I not go through all the equation because I believe you have learned it before. And basically we have the displacement in terms of the real coordinate x and y, and we want to take the derivative of the displacement in terms of the natural coordinate. So we use a chain rules. When we use a chain rules, right, we can just rearrange the term in the metric and the vector forms. We have in one column, which is the derivative of the u and v. This is u and v, right? Let me have a look. Sorry, this is the derivative of the u in terms of the natural curses and in terms of the natural eta terms. And by doing this, you can make the relationship between the first derivative of the displacement, any displacement function, in terms of the natural coordinate to match with the coordinate in x, the natural coordinate in the coordinate in y. And we take the inverse, and this what we call the Jacobian matrix. We take the inverse of the Jacobian matrix. You can get the transformations from the real coordinate to be the natural coordinate. By simply rearrange this term, this concept, we can have this as a transformations. And the less is the same as what you derived before for the bilinear function. And this is how we defining the Jacobian. So because we use the standard isoparametric, so we define the function of the coordinate and the function of the displacement with the same shape function. This is the meaning of the isoparametric. So we define the geometry and we define the displacement by using the same shape function. So that's why we call them as an isoparametric. Iso is the same. And that's why we can simply derive the Jacobian terms by taking the first derivative, right? And we define the real coordinate in terms of the shape function, and this is the coordinate in the nodal that we've used, and we represent them So we carry on to this. So the purpose is we want to construct the stiffness matrix, and this is what we discussed from last week. And we had the CALFEMs, and we just want to talk as well. Okay, you have already set up the K stiffness matrix. You need the force matrix as well. The force is if you have the force applied at the boundaries, and it's a linear force, it's easy because you can just simply use the average areas between the node, right? And time with the values of the force. Somehow, if you have the nonlinear force function, to get the force to be allocated to each of the node, you need to take the integrations of the force term to the shape function transport, right, over the range that you're looking at in terms of a single dimensions. If you look at it in the two-dimension x and y, you need to take double integration, and you define the function of the force. For example, we have one problem, which is the sail wedge of the concrete dam in the plane strain. You define the gravity of the dam, the density of the dams, that giving in terms of the force per unit areas, right? And you time with the thickness, which is we giving as a 0.1. And by having this, so you can use a double integration to derive, right, when you integrate over the area over here, how much of the force should be applied at the coordinate of each node as per element. And when you assemble all the elements together, the way how we assemble them is simple. So the force value that's shared within the same node, within the same degree of freedom, you just combine them, right? You just keep add them up. The way how it works is you have to calculate the force for individual element to transform all the force function, right? Either in the as a line load or as a load over the areas to be the nodal force applied at each degree of freedom that you're looking at. If it is a line, the distributed load over the line or over the boundary of the element, you just take the integration over the line, which is from the distance of negative a to a, right? Very simple. And then you just get the what's it called, the nodal force. And don't forget the positive direction of the nodal force. Follow the direction of the degree of freedom always. And if you're looking at the force that distribute in two-dimensional space, such as the sail wedge or the body wedge of the structures, in which you have the load as a pressure, the pressure is the force per unit areas, and you're saying that you want to obtain the force in the four node, so you use the four node shape function and you take double integration. The double integration is for you take the integrate over the x-axis and over the y-axis, so you cover for the whole area as per element. So once you do that, you get the nodal force that apply to each of the coordinate, and you keep it, and you do it by element, and when you assemble them, you just combine the force that apply in the same degree of freedom, and you just add them up until you get the whole global force matrix, which is RE. Once you get RE, you get KU. You just make sure that this one is non-singular matrix, so it's stable, right? And there are a lot of issues that we can check for the K matrix, especially if you want to looking at the nonlinear behavior of the structure, what we don't cover in this course here. We can check the property of the matrix. There are a couple of the property that we can check, for example, whether the matrix is called as a definiteness or indefiniteness. But I don't want to go to the details. We talk about whether it's stable or unstable by looking at the property of that. But in the beginning, we just say that if it can be inversible for the elastic analysis, it is non-singular matrix. Basically, the matrix is stable. The structure you look at is stable. So you have enough boundary condition or the support condition. you take the inverse and to the force matrix that you assemble for the whole element or for the whole structures, you obtain the value of the displacement. The displacement we go for each of the degree of freedom. And how we use this displacement? You have to take this displacement and just send them back to each of the element. And each element you got 4 nodes, you've got 8 degree of freedom. So you have to allocate the set of the actual degree, the displacement and the degree of freedom to the nodal degree of freedom of each element. So each element is got 8 nodes. You got the value of the displacement, which is 8 of the displacement according to the displacement at the element. So after that, you can obtain the value of the strain. How you obtain the value of the strain is very simple. You use this formulation. And the hook law, when you assemble them, you got B, which is equal to 3/8, right? So you know how you obtain this. And this is corresponding to the B at the 4 node, right? You assemble for the element wise, and you already solve for U, and you send the data of the results that the displacement at each of the degree of freedom as per element. You got 8 degree of freedom, and you put them in D. Right, you take the D, which is the real displacement, and the nodal time to the discretized B matrix, which is the derivative of the shape function. You obtain the values of the strain. If you want to obtain the value of the stress as per element, you just take the strain times to the stiffness to get the stress values, right? And this is the way how it's worked. Okay. And so what we do here is that I'm sure you know how to get this done. And because we use the numerical integrations, when you use a numerical integration, the stress value that we have here as per element, let me explain to you. We have the value of the stress and the strain at the Gauss point. So it's depend on how you use the numerical integration. So what the meaning of the stress at the Gauss point? It is an approximation. Let me explain to you. And that will lead to how can we make sure that our discretization is work or it doesn't work. The meaning of the stress and the Gauss point. So what it really mean is that if I'm looking at one of the problem that we have and we are setting up, which is the notch problem. So you have the rectangular specimens. And assuming that we have them in the 3-dimensional space. So what we do, right, in this problem, we having a force, which is the UDL or the uniform pressure over the thickness of the on each side. The forces that we have here is saying that this is the I cannot remember what I said. Is it alpha, right? Yeah. it says it's an alpha. So it might be some type of the function of alphas. Let's say, according to this example. And this is the sums of the applied force. And what is happened, this is the real structure you'll be looking at, and how we want to solve them. We want to apply the concept of the finite element. So in the beginning, I want to discretize them by using the information of the symmetry. We have double symmetry of the problems. So I said I take them to be half. And I just want to model them in a quarters. We have two symmetry lines. So what is happened by doing this, I'm saying that the response of each quarter will be the mirror image for each of them. For example, if I'm looking at the symmetry about the y-axis, the response of the notch problem here will be similar to the response over there, but it's in the opposite side. It's like the mirror image of each other. The response of the specimen at the top part will be identical to the one at the bottom in the opposite side. So it's a mirror image of each other. So it will be identical. So that's why, as I mentioned before, we don't need to model this problem as a whole. We just deciding to model the problems by taking only a quarter of this. When we deciding that we want to model only the quarter, we have to identify the boundary condition. This is the first thing. When we identify the boundary condition, what we see is that this is the boundary that we share the areas at the top and the sides. So when we're sharing this area, because the behavior of them is like the mirror image between them. So what we do, we know that, okay, it's got the restraint conditions over the boundaries here. So what is mean to make it to be the mirror image? So there is no translation in this direction. So the any line here is the line of the zero movement in the vertical direction. So if I'm saying that this is in the axis of, I'm set them here, which is x, y, and z. So I'm saying that along the symmetry lines over the x-axis, the displacement along this line here equal to 0, based on the boundary condition we know. And on the other side, it's also come with another boundary condition where it's sharing, is having the mirror image about the y-axis. So we can imply that along the line here, except up to the crack, we restrain the displacement about the y-axis, or ux had to be equal to 0, so that the double symmetry can be applied. So I'm saying here that ux, right. So by having this, So what we do, we can now taking this out. And we can put into our structure model. And we expand them, make it big, because we want to investigate the behavior of the notch. So let me clear this up. We don't need this actually. And now we want to do the structure model of this one here, only a quarter. So let me enlarge this figure a bit more. And because we assuming that this problem is a thin thread specimen, and the thickness of this, we state that we saying is equal to T, and we saying that T is so thin. So that's why we can simplify the problems to become the plane stress. When we say that the plane stress, as I mentioned before, this is mean that all the stress in the out of plane equal to 0. So we can apply, we can assume to be plane stress. And when we want to model these problems, we have an applied force, and the force will depend on how many mesh we want. And in the beginnings, I want to make it as a cost mesh. The cost mesh, what it means is this. I want to put the dot, which is the nodes we have here, by just split the structure to be, I try to remain my structure to be a square as much as possible. But of course, this is a bit hard. So let me rearrange them. Assuming that this is the structures we have here. And I put the node first, then I connect the node with the line. Along the line that we connect the node through, this one start to form the element for us. If we're doing this, there is a problem. Can you identify the problems here? Because we don't allocate the node here. The problem is that when we have two other finite element, right? If you have a look, if we don't allocate the node at this point, the element that you have, and of course, sorry, this one we have the, you can try the 4 node, right? It's possible that you can do the 4 node here, right? But because I draw is too much to the triangle, but in our problem, this is not the triangle. In our problem, this is more or less is like a square. So that's why you can allocate the node. And thing that you have to be careful is that the ratio of the mesh assuming that you're having, which is B, this is H, and I'm saying that B over H have to be right at the minimums is 1/2, where you're having B is less than or equal to H. We try to have an aspect ratio of the element not to be too much stiff. So this one is not good because if you have a look here, you have the ratio of B over H more than half. Sorry, less than half, right? It's too stiff. So that's why I take this out to make it close to the square as much as possible. But if I'm doing this, what is happened? You see that we have allocate the node. So we have to remove them because otherwise we have the hanging node. I will explain the concept of the hanging node later, but let me remove this. This is, we don't need it anymore. So I was deciding to remove the node. But I decided to remove the node here as well. And when we're removing, we can also remove the boundary as well, but we don't need it anymore. Just give me a bit time. And then what we do, we connect the element between the node. Because we have this pattern of the node here, so this one we can remove. And we put the boundary condition only to the node by, this is saying that, okay, we want to allocate the restraint point in this node and in this directions. Similarly for the restraint on the other side, so we don't need this anymore. And remove this. I put the restraint. All right, so we got the element. This is not more or less. This is our very standard, and it might be the very simple element that you can have. And if you want to make it to be nicer, you should allocate the space between the element to be the same. Right, in this case, you can do so, you just move the node. So that you will have the distribution of the stress and you have the nice mesh. Normally the nice mesh is a uniform mesh, right? But it's normally it's take and it's consume a lot of the computing effort. This is the basic property that you have to satisfy. And we already allocate the what is called the boundary conditions. And what you do next, you have to put in the degree of freedom. The rest of it is just what you similar to what you did before. Is that you allocate the node number. I normally put it in the order, start from the rows, because later on I can see the series of them. And what I do, right? Normally I will looking at the geometry. For example, this is the total half of the length. This may be L, and another half of the depth. This might be B. And I don't use B, I use L1 and L2. And I might say that I want to divide the spacings of the element to be equal, right? Assume that this is to be equal. And if we want 4 elements along the length, the distance of this, you just take it to be equal divided by 4. And this one as well. I just want 2 elements and I want to have it as a uniform mesh. And I take it to be, and this is L1, sorry, this is L2. L2. And this is L1. Because we want 2 elements. And what you do, right, you got the information of the node, you got the geometry of the node, and then you just allocate the element, you just define the element in the counterclockwise. So I'm saying that I started from 1, 2, in each of the element is a 1, 2, 6, 7, 2, 3, 7, 8, 3, 4, sorry, not 7, 8 is wrong. Is it wrong? I have to follow in the anti-clockwise. 8, 9, 10, 9, 6, 7, 12, 11. You might see the pattern that the numbers start to have some repeating pattern. So that's why when you have to discretize them, you don't need to do it by hand. You can just have the MATLAB to run or to generate the number for you. Right. For example, I know that this is the element number 1, element number 2, element number 3, 4, 5, 6, 7, and 8. And I say that the element number 1 is start from 1, 2, 7, 6, 2, 2, 3, 8, 7. And you see that the pattern of it start from this number, and you just keep increasing the value of the node by 1, right? So you can have this repeating pattern. And if you have 100 of the element along the line here, so you know how it is, you just need to tell the coordinate of each one. But if you put into the systematic way, when you want to discretize the element, you can use the MATLAB with the pattern of the number. This is most of the structure digitization they do. We make it simple. Once you have the geometry of the mesh, you can also, when you define the node, you tell what is the degree of freedom that come with them. For example, I'm saying that, okay, at the node number 1, we have this pattern of degree of freedom 1, 2. Node number 2, I have 3, 4, and you keep running the degree of freedom number 5, 5, 6, and so on. Right up to this one here, you having is 9, 10. And if you go on the second line, you have in 11, 12. You go to the end, you having, this is the 19 and 20 and so on. Right. And you can just tell them that which degree of freedom it has been restrained and which one hasn't been restrained, right? And this one, you know that the condition at this degree of freedom 19, so which is a u at the degree of freedom 19 is equal to 0. So this is mean this degree of freedom is you don't have the degree of freedom. You can skip it, right? But you can arrange them by somehow, not too difficult, right? But you can guess the pattern of the number that you have. This is 21, 22, and up to 29, 30. So you see the repeating pattern, and you just allocate that. Okay, there are some degree of freedom, for example, 22, and the vertical degree of freedom at the node 12, 13, 14, and 15 has been restrained, and so on. So by having this, you can start to have the geometry of the coordinate, right? When you put in the coordinate 1, 2, 3 up to 15, you can have the connectivity, which is the EDOF, which is the connectivities of the element, by telling how the element has been formed according to the node. And you can allocate the degree of freedom corresponding to each node. And that is required in the CALFEM, the input of the CALFEMs. The input that I sent to you last week is a hook, not the hook, is called as, let me have a look. The example is a hook example. Let me have a look. It's a hook, not hook, sorry. So I think I show you the geometry of them. So what you can see is here, I tell you the coordinate as well. I think you can trace the information of how we can make and input files, right, from the EDOF. The DOF is a degree of freedoms where we have restrained the support here, which is the cantilever beams. So we don't allow the translation along the node in the left-hand side line. So we give them as a 0 degree of freedom. And then we keep running the number of degree of freedom. When we give the coordinate number, right, which is how we tell the geometry of each node, and then we give the force information. So by having this, you can just take it as an input to the CALFEMs, which is you should not have problem on this. And let me talk about the concept of when we have the information of the stress at the Gauss point. Because when you solve the problem, the stress value that you have is corresponding to the Gauss point, and the strain value that you have is corresponding to the Gauss point as well. When we solve for the stress at the Gauss point, what is really mean is this: because we use the numerical integrations. So let me move this to the corner, and let me shift this up. When we looking at each of the element, assuming that we take and we want to investigate the stress at the element, And the element, each of the element has been approximate, right, by taking divide, basically they divide them by using the quadrature rules. So they divide them to be 4. And the information of any stress value that corresponding to what you can solve from the finite element package, which is derived from the displacement fields, it's giving you the information of the stress in the Gauss point. It's allocated at 1 over the square root 3 from the edge, right, on each of the edge. And how is this Gauss point is representing? Because we use the quadrature rules. And this is the location of the stress over the plane areas that they use, and they use in the approximation of the stress values at the quarters. When we take the integration by taking the Gauss point, so what it means is that the distribution of the stress normally is a nonlinear distribution, right? Assuming that we plot this one as well, and we plot them in the 3-dimensional space. And I'm saying that we subdivide them. And the distribution of the stress, for example, to what we want to investigate, this might be in the highly nonlinear pattern. So this might be the surface. This might be the surface of the distribution of the stress. But when we use a Gauss point, the Gauss integration rules, so what is happening? We represent the surface of the, we see the stress surface of, if you use the displacement fields, this is the approximation of the displacement, the field of the displacement at the Gauss point. But this one is saying that, okay, we capture the information of the stress at the Gauss point. This is my Gauss point is here. So what is happened is project the stress up to the line of the surface. And then they're saying that the whole block of the quarter areas that we're looking at is take the value of the average stress in these areas. And the stress value that they take is coming from the Gauss point. So you approximate the stress, not the whole surface, but you discretize the whole surface by using the information of the fixed stress at the Gauss point. Similarly, we have another stress value to the Gauss point, so it might project the stress value up to these levels. Then you can do the projection of so you're seeing that we try to approximate the nonlinear stress value by using some type of the fixed graph or the fixed values. And we keep, so the information to report to you from the finite element is the approximation. Right. So this might be, the Gauss point might represent the stress value here. And I'm saying that this is the real surface of the stress response in X and Y. But this is when you obtain the stress values, which is the approximations at the Gauss point. You may have the Gauss point number 1 you may have the Gauss point number 2, you may have the Gauss point number 3, and so on. This project just approximate the value of the stress. So I try to draw in the really nice graphics. Hope it's work. Then what is happened? All the point, the stress value that you obtain from the finite element is just an approximate, not the real. This might be at the Gauss point number 4. So when we want to fit the graph, the idea is that the more that we have the number of the Gauss point or the point of the representative stresses in the element, the better of the results you have, right? So that's why there are a couple of the effort that people try to do, right? One of the way they try to allocate more number of the Gauss point inside the domain or the element mode domain. But by having more number of the Gauss point, it's not simply just put the Gauss point allocation in. You have to increase the level of the nonlinear function you use. So basically, there is the relationship between the orders of the shape function. If you use a bilinear shape function, you are allowed to use only 2 by 2 Gauss point. If you use the quadratic shape function, you can use perhaps up to x Gauss point. So there is a rule, which is that theoretically there has been proved that how many Gauss point is we work for what type of the order function you look in the what's it called in the displacement field that you assume, right? The more that you increase the order of the displacement fields. So it means rather than you use a linear shape function, you use a non-linear shape function, the more of the accuracy that you have, but of course it will take more computing effort. So that's why in the area of the finite element, people try to develop the robust element. The robust element is mean it doesn't need much of the information. You can approximate the value of the stresses, right? You see that by using the Gauss point, so you just approximate them as a linear surface, but we want the nonlinear hypersurface. This is the nonlinear hypersurface, but we use a linear surface to approximate the nonlinear hypersurface, right? Then the value of the Gauss points normally is returning you with the set, right? To what I try to say is here, let me show you. This is coming as a set of the stress tensor, which is sigma x, sigma y, and the tau xy. And each of the Gauss point is become with this set of the stress tensor as well. For example, taking the Gauss point number 1 is become with the set of the sigma xx, sigma y, and the tau xy at the Gauss point 1, and so on, right? So I'm not going to explain, write them more. And in the material property, they try to use the information of the stresses to describe the behavior of the materials. And one of them, we call them as a von Mises materials. We have the von Mises materials. The von Mises materials is one of the very popular one that we use to describe the behavior of the ductile materials. One of the example of the ductile material is a steel. It's used in the in describing the behavior of the steel, right? And giving the information or the formulation of the von Mises stresses, right? You just take the information of the stress, the resulting stress, or you take the stress at the Gauss point, and that value of the stress at the Gauss point will represent the approximation at each quarter of the element to what I say, right, as a constant. So we approximate the hypersurface stresses by using the piecewise constant fields of the stress that we have at the Gauss point. Okay, and this is the meaning of it. So when we start to, I can say something a bit more here if you want to. Remember the concept of the Gauss quadratures. If you recall, we had the very simple basic mathematics. And I'm saying that I want to describe the nonlinear function. And this is in terms of the y in terms of x is a function this can be described, so this can be described as y as a function of x. This is the nonlinear surface in the plane. When we use a Gauss point, which is the integration rules and the finite element concept, is as follows. Hope you can see. If you don't understand, let me know. Okay, I try to explain in the way that I understand it. When I want to I want to approximate the nonlinear curve over the range here. So I have a couple of the options that we can do. The first option is that I split them. Listen to me first. I split them to be 4 or 3 piecewise portion. So what it means, I discretize them to be, right, assuming that this is the same length, L, L, and L. And because this one has been described in the nonlinear functions, I can, within each of the portion, which is the length, let's say this is the node number 1, this is the node number 2, the node number 3, the node number 4. This is the proportion or the portion number 1, or you can record it as an element if you want, and portion number 3. And we use some type of the approximation at the finite element. Then we use a Gauss point integration. So what is happened? I say that okay, we assume it's 2 Gauss point, right? And the value of the approximation that we have is just represents the half of the surface lines here, right? And we do so. This is at half. This is assuming this is the information that I obtained on the curve. Right. And so you're seeing that if I want to find the information of the areas, the area is the integration of the over x of the function fx. So basically, I trying to find the areas underneath the nonlinear curve over here. But if we use some type of the approximations, it is the summations of the areas for each of the linear proportion that I discretize them from 1 to 3. And in each proportion is giving me the approximation of the areas in the linears, which is the constant. For example, at the Gauss point number 1, this is at the Gauss point number 2, number 1, number 2, and so on. So then what it means is trying to find the sums of the areas at the Gauss point number 1 of the element 1 plus that's the Gauss point number 2 of the element 1, and I add them. For these 3 elements. By having this type of the approximation to get the area underneath the curve, to get the more accurate, so what you do, you have 2 options. One, to put more number of the Gauss point to approximate the curve, or the other, you discretize the structure to be more, right? The more that you subdivide the portion to have from 3 to be 6, 6 to be 12, to be 24. So you start to get the value of this closer to what actually required here, which is the real solution. Similarly to the concept of the finite element, because you knowing that when we use the finite element, we try to approximate the behavior of the structure by assuming the displacement function. That's why we call them as a displacement field. So it can capture the displacement quite okay, but the value of the force or the stress field is not good. So that's why when we derive it from the displacement fields, we cannot perform the closed form integration. So we have to use the approximate integration. So that's why we use the concept of the Gauss point. We use the concept of the Gauss point, so it means we try to approximate the hyperplane, which is a non-linear, by using the constant plane of the linear within the element, right? So the more the Gauss point, the more of the element, and of course, when you increase the number of the Gauss point, you have to increase the function of the displacement and so on, the more accuracy you have here. But in our example, we try to fix. We assume that we use a standard isoparametrics. And the function we use the bilinear element. So when we say that this is a bilinear element, so it's fixed the number of Gauss points to be 2 by 2 in the plane problem, right? So we could not use more number of Gauss points. So the only option we have left to get more accurate results to fit the hyperplane of the curve is we have to discretize more element, right? The way how we can do the more discretization of the element is as follows. If I want to discretize more from egg element we have here, I can simply subdivide them along the length by half. But if I subdivide them by half, what has happened is start to violate the ratio. This has been put as a must that you should not have the ratio of the shortest size to the longest size more than half, right? So to make it to be as a nice mesh, so we have to discretize them along the line here as well. So once we're doing this, what is happen, it will split the number of the element from 8 to become 32. How to become 32? Because each of the element can be subdivided into 4. So you use 8 times 4, you got 32, sorry, 32, right? And if you're not satisfied enough, you can split more. For example, I am not satisfied enough. I'm saying that, okay, I want to investigate the stress along these regions here. The reason for this is because by the theoretical concept is saying that the distribution of the stress when it's close to the crack tip, this is the crack tips, it will generate the huge value of the stress. We call them as the non-smoothness of the stress, the jump of the stress in these regions. So there is a sudden change in the value of the stresses at the crack tip. So is it happen this way? For us to approximate the stress to be more accurate, so we need more number of the element over the crack tip. So over the crack tip is require a lot more number of the elements, right? So that's why this is depend on. Sometimes I will show you the nice element later, right? But in most of the thing is that when we find the problem is this notch, the crack tip is a problem. So you need more number of the element around the crack tip to approximate the sudden change or the high variation of the stresses, so that if we perform the high order of the variation of the stress for this. So to satisfy this, so I need to discretize this area more. So what we do, definitely, I deciding to cut more, divide more the element in these areas. So you might see that to make it compatible, when I discretize over these regions, it will make the node here. You see, it's clear, right? When it having the node here, and if we don't discretize the element which is in the neighbor element, this element cannot be formed, because this one we call them, we have 5 nodes. The 5 node, if you come and match with the 4 node, is we create the problem. The problem that we find for this 5 node, we call them as a hanging node, which is we don't want it to happen. So how the hanging node is work? If I take this out and I show you that we have this is an element that we discretize it, and we have the node. This is for the 4 node, and this is we have 5 node. The hanging node will have the incompatible over the regions here, because over this information we have 4 node, the movement is at the degree of freedom, right? But in this element is only connect to the top 2 element at the node. So this element, it doesn't connect to the node. So what is happened when we plot the deformations, we will see that there is the opening of the surface, because this one can deform. This can deform it might deform. But when the top element is deformed, you're seeing that because the bottom element, you only have the node over here, and we lack of the node in the middle of the surface over there. So that's why when it deforms, it has to be as a straight line. So it can open up the gaps over here. So we call them as a hanging node. And we don't, in any of the finite element, we don't want to have the hanging node. The hanging node is not allowed because you don't have the full compatible of the element. So what we do for this case, you have to keep subdividing. You have two options. Let me explain to you. You have to keep subdividing. What's it happening? The elements until you reach to the bottom, right? And when you discretize this element, you have to keep doing this. And if you keep doing this, you have to go along the way to stop the hanging node. And when you have this aspect ratio of the element, it doesn't look nice because it will make it above 1:2. So one of the things that you can use it and it can solve for the hanging node is as follows. You can have use the spatial geometry of the element. So let me reverse. The spatial geometry of the element that I suggest for you to use is that you can try in this case also as another transformation of the element. So let me remove this. So I don't want this to be removed. So I come to the other side then. There is another pattern that you can transform. You can discretize the structure a bit better. We have another pattern of the structural discretization, which is you can make them to be a non-square, but in the trapezoid shape. Right. So in this, the nice thing of this is that you can transform, listen to me first, you can have the transformation of the element in this pattern. So you have 1, 2, 3, 4 elements. This is the transformation of the element. So that can make the structural discretization from a single element like this, which is the one I just draw here, to become 3 of the element. So we need some certain set of the transformation. So we call them the transformation. So by having this, you're seeing that you don't have the hanging node at all. You see the information of the node still complete, very nice, true. we stop the problem with the Hanky node totally, because everything you can transform, start from the single element, and you can subdivide them to be 3 elements straight away by having this pattern, and every element that you have is a 4 node, right? And this is a nice, so you have to use some type of transformation. Otherwise when you subdivide element, you have to subdivide as a whole, right? So this is the painful of it. So if we're looking at our problems, so what I suggest to you is that in this case, because it's quite simple, you can just try and subdivide the element by using the uniform discretizations. So you might start from the 4 and you subdivide them to be 16, and you time 4 again until you get the more accurate results. And how do you know that you should stop the structural discretization is as follows. Because what we do here, we try to approximate the stress value and so on. Let me capture this. Assuming that you are looking at the notch problem again, and don't forget, every time, this is important, every time when you subdivide the element, don't forget that you have the information of the forces, and the force applied to the node will be discretized as well, the value of them. Right. So don't forget, for example, if I have is a 0.00.288 alpha, so the sum of the nodal force along the line here had to be equal to, because we just take by half, 0.144. Alpha is a constant depending on the group number you're looking at. So this is the sum of the forces. The force RE. Right. So the more that you discretize a problem, and what we ask you in this problem, you have a look. I'm saying that, okay, we like to know the informations of the forces that you apply here. And where is it? Yeah. I like you to plot the relationship between the force that you apply, and you obtain the displacement and the stresses. We like to know how much of the displacement you can obtain. The displacement here is at the center, because I cut this is from a quarter. So this is the displacement we're looking at. So we want to know the information of the deformations in this case, because this is at the restraint point. We want to know the deformations at the centers here. We'd like to know how much of the displacement, but every time when you discretize an element, you use the informations, which is the vector of RE equal to the K matrix, and you obtain the value of G, which is the displacement, and you just extract the displacement to be associated with the degree of freedom, and this is the lateral displacement. So to make sure that how you can obtain the accurate values, you should test the element. The way how we test the element is that in this exercise, we suggest you to use the displacement value as some specific degree of freedom. And in this assignment, we told you and you plot them versus to the number of elements you use, or the finite element number you use. For example, in the beginning, you start from the finite with the 4 number of the element, right? In this example, or egg, sorry, I use egg. And you solve for the displacement, you obtain this value. And you discretize more. For example, you next time you discretize them to be 32, you obtain another displacement value. And the more that you discretize an element, right, is supposed to be that 128 and more. The more that you discretize the element, the more of the accurate result that you should obtain until it's converged to the flat curve. So this is to be sure that the results that you have here is converged. Right. So we want to obtain it until it's converged to some value. So if it converges to some values, so you're saying that, okay, it's converged already. So then the certain set of the element you use is might be how many elements, I'm not sure, that you use in this scenario is good enough. So you have to plot this, is called as a convergence curve, right? So it's converged. So each of the problem, you have 3 problems, you have to try and discretize an element. Every time you discretize an element, it should converge to the real solution because this is an approximation. Remember the curve here, you have this, it might be the real solution. So the more you discretize the element, is try to fit the curve well, right? So I think that should be all to what I should cover. So in this exercise, they ask you to have a look. They ask you to check the convergence, right? The CALFEM can tell this, yes. You determine the value of the displacement at the degree of freedom that's specified directly in the figure. In this figure here, we said that this is the displacement at the centers. And in this figure, it is the displacement at the center lines here. And in this figure, it is the displacement at the bottom where it's uplift. So the concrete dam might try to lift up. So when it lift up, this will open. You may have, when you plot the deformed curve, you may have it pretty much look like this. So we want to see how much of the uplift. So you have to test the convergence of the node or of the mesh you have. That's why I say that you have to test the convergence of the mesh, right, to obtain the sufficient accurate value of the displacement. So each of the problem you look at, you have to discretize the problem more, because finite means approximation method, right? So it's not the closed form solution. So to get the best one, you have to discretize more. And then based on the mesh that you take, and that give you the accurate results, what I ask you to do, you have to plot the equivalent von Mises stresses at the Gauss point, and you can plot the variation that in the MATLAB they got the how to plot the color to show the variation of the value, because the von Mises stresses can be calculated by using these formulations here. And that is based on the stress tensor that you obtain at the Gauss point. So you had to calculate the volume stress, either the plane stress and plane strain, you calculate at Gauss point. Right. So each element you have for Gauss point. I think that should be all for the exercise you have. Any question first, please?
อาจารย์ครับ
ครับ
อย่าง convergence เนี่ย tolerance ควรจะอยู่ที่ประมาณเท่าไหร่ครับแบบว่าแบบ iteration ประมาณครั้งต่อไปที่เราจะหยุด iteration เนี่ยอาจารย์คิดว่าประมาณมันต้องอยู่ประมาณเท่าไหร่ครับ
It's depend. The question, okay, the ผมตอบนะครับ the question that this is a good questions. The question that your friend asked is that what is the tolerance? So it means that the chain, the tolerance mean the small chain when you keep digitizing the element. So it doesn't need to be much. Normally what we do, we just see the graph and it start to converge close to the flat, right? That's why I draw the flat curve. If it approach the flat curve here, so I think that is good enough. Because sometimes if you use a very small tolerance, you need to perform so much number of the mesh. When you take so much number of the meshes, what has happened is consume a lot of the computing times, right? So this is the tolerance, you just pick it, right? And normally take in just a not too small decimal, it might be, because each one of them is depend because the value of the displacement is different for each one of them. Normally I look at the curve, I don't set the tolerance. So when I test it, I see that, okay, it starts to be flat now. So I said, okay, this should be good. And then I stop. All right, but this is depend on your judgment. And if you want to look at it in the research fields, of course, in the research fields, they will stop it until it's close to the very flat. But that is mean they use a very robust element because when it go to the very flat curve, the number of the element will be huge. And when it's huge, it takes a lot of computing effort, right? So this one you have to figure out. And let me show you something. I stop sharing this. Just hold a second. Hold on. Okay. Let me show you this. This is my paper that I published last year. Excuse me. It's about the special element that I have developed with my postgrad student. And the idea is very simple. I use a bilinear, but the way how we develop, I use some special technique to define the new element, right? But every time when we develop the new finite element, the thing is that we have to show the nice properties of the element. The nice property of the element is the punch. You see, I start from the very coarse mesh. The mesh is not much because it's a coarse mesh, but I run the nonlinear analysis as well. But when we check the accuracy, you see that we talk in terms of the number of the element and we compare with the accuracies. And you're seeing that to what I mentioned to you is if you do the uniform mesh, this is the uniform mesh. You see that the way how I subdivide the element is like you just draw the grid line and the size of the grid line is so small. And to make when we check this, to get the accuracy, of course, we have the benchmark to compare, and we plot the convergence curve as well to what I showed you before. And the nice thing is that the more that you discretize the mesh, you see that the smoother of the distribution of the displacement of the stresses, this is the one measure stresses, it's going to show you. So the one measure stresses, it shows the behavior of the stress transfer. We have the foundation of the uniform pressure applied, right? I just model them as a half of the punch problem. So this is the boundary of the structure you're looking at. So I take only half of them. So the loading will be somewhere that I put my hand on. And when I push the loading, you see that it's deformed. And if we push, it has the push-pull effect. We have the push here, it transforms the stresses to the adjacent. So that's why it's hop up over there. So, and the stress value has been shown, right? And I clamp them. So I fix the boundary. You see that the boundary doesn't move at all. And I define the boundary at the center. The boundary at the center, it doesn't allow the translation in the x-axis. So the more that we discretize the element, of course, you have the better idea and the stress start to converge. So, but when we check the convergence, right? This is another notch problems. I think I have the convergence graph somewhere. And you see the smoother of the curve we have. And you see that the more, if you plot the deformed shape, when you plot the deformed shape and when you have the good mesh, the mesh when it's deformed, it will show the failure line to you. You see that this is where the stress has been jumped a lot. You can show and you can compare them here. You see that? So it's follow the pattern of the stresses. And I have the convergent graph somewhere. Not this one, sorry, but I have another paper which is published in the same year. And with that, I use another technique. There are so many techniques for the finite element. One of the techniques that people use a lot, and it has been very popular, and we call it a smart mesh. The smart mesh means the mesh can subdivide itself. So it can adjust the number of the mesh itself. So the element that I propose and is in the active area, so that the area where you have the huge intensity of the stresses, we have the huge value and the huge variation, the changes of the stresses in some of the small areas, it requires a lot of the measures in that areas. But where you have the uniform mesh, it doesn't require the mesh. So if you want to do the uniform refinement, right, for this type of problem, you will have the problem that you have to refine the mesh so very tiny for the whole domain, and it take a lot of the effort, right? You can have up to 100,000 or million of the measures. But if you use the smart mesh means you can decide whether which element you want to discretize the mesh, which element you want to combine the mesh. It can combine, it's like a cell. The cell can split itself, the cell can combine itself to where it's required. So that's why we use this technique, and we just let the element, you see, this is the convergent curve that I plot. You see that I didn't go too very far. I said, okay, this is close to the flat, and then I stop. But what I show in this, my research, is you see that I compare between the uniform mesh, and if I want to use the concept of the automatic adaptive mesh, so the mesh can define by itself that which area when there is a huge variation of the stresses, they will keep discretized in those areas. And the purpose, you might notice that I didn't use a 4-node, I use a 3-node, because the 3-node is very flexible for forming the shape of arbitrary structures. So that's why I use a 3-node. But as you know, the shape function of the 3-node is a constant shape function, and it's very poor element. Very poor, it means it requires a lot of the element to get the good accuracy. So, but I developed another type of element which is a node based. So I define the parameter different way, as the isoparametric or the 3-node element normally has been divided, but it's worked very well, right? You see that. So this is still in the active areas, right? The perp, you see it can adjust, rather than you have the uniform, you compare with the non-uniform mesh, right? And it saves a lot of the computing effort, especially when you have the curve as a whole, or you have the curve boundary and so on. When you have the non-uniform mesh, it saves a lot of the computing effort, because it's only define the element where it's actually required. right? Where it requires you looking at the intensity of the stresses. The blue one is a high stress value. Sorry, it's a uniform. The red one is a high stress value, so it's keep adjusting where there is the jump in the stresses. So it's determined in those areas. And so this is not the thing I plot here is not the in my exercise. It's not the straight value. I plot the Young modulus, right? But I use the elastic analysis. When the Young modulus is start to be low, so it means the stress start to develop up to the plastic stress. When the Young modulus is high, it's an elastic stress, right? You just think about the stress strain curve. In the beginning, you have the huge value, the high value of the Young modulus because it's still elastic. When it start to lose the elasticity, it start the value of the Young modulus start to be dropped. So it's close to zero. When it's zero, so you're on the flat curve. So that's why when I plot here, I plot the value of the modulus variation. But on the other hand, this can represent the stress value as well, right? The stress will be at the blue line, which is the high stress. The red line will be just the uniform stress, which is the elastic stresses. So this is in there. You're seeing that just the element by itself can tell you where the failure is, right? But you don't without having looking at the stress value, because it can determine the failure straight away when you have arbitrary shape of the structures. And when you have this is the deformations, right? And this is the half of the ring, and I put the damage too, and you see that the variation of stress in the tiny areas can be captured with a very nice non-uniform mesh. Okay, so what I try, so come back to our exercise. So you might see in the advanced research and what you are beginning now, what you are start looking at now. The concept that I show you and I talk to you in these 2 weeks, as I mentioned before, I just want to introduce you to some of the very principle, the basic element that people use. And I hope, with my hope that you will take some times, even I give you most of the code and it will work, I'm sure, because I try many times. And you just change the input, of course. But if you want to go and start in deep, and this is for the sake of your knowledge, and I suggest so, if you can looking at how the way you just have the basic equation force equal to the K matrix times with the displacement vectors, and you look at how it's assembled, you understand well, because when you look at the finite element, it's hard for looking at the hand calculation. It's almost impossible to do the hand calculation, even for the small example. The best way to learn the finite element is you have to look into the code, and you can understand the very basic, which is a MATLAB code, and you have the background already, because we already discussed a MATLAB in the last semester. And you understand the way how they assemble, they understand the way how it's worked. And this is the door that is open to you, that you can use the tools, the advanced tools. There are so many advanced tools that are available in the commercial package, or you can develop the tool by yourself. But as long as you understand the concept, you can even develop the element of yourself as well. Right, and the CALFEM that I gave to you guys did not develop by myself, but it developed by the big group, I think in Netherlands, and it's very easy, very robust, very very precise in the way how they return the code, right? So that's why I think this exercise is quite useful to you guys. I not say that you will waste the time on this. So I see that the more that you learn, the better that you are, right? And in my part, that's it to what I have, and I share with you for these 2 weeks. And I hope that you can submit your assignment with your learning progress, right? And in my part, we don't have the exams, just for report as a group report. All right. So I hope that answered you well. Any question further, please? And I hope you see the useful and the advantage of nowadays people use finite element. If I can share you with a story in about 30-40 years ago, there are two fields of people when they're looking into the analysis field, which is one is called as a closed form formulations or the numerical formulation. The other one is a discrete method, which is the finite element is a discrete method approximation. In the 40 years ago, finite element is not popular because as you can see, it is a metric analysis method, and to get the accurate results, you need a lot of the effort to take the linear algebra operation to inverse a matrix, to time the vector to the matrix, and so on, to assemble and so on. On the other hand, 50 years ago, the analytical solution is easy. It's not easy, but it has been very advanced, and you can use some type of the numerical approximation technique to do the integration, to form the closed form formulation. But those limit the application of it, because you can derive the formulation, you can find the closed form solution of the problem only for the academic problem. You cannot solve for the high-rise building. But the game changer has become in the last 30 years ago, when we have the what is called as a computer, which is the personal computer, not the supercomputer. Once we have the supercomputer, let's say like the desktop or the laptop that you have, you can just do the solution for the linear metric algebra for yourselves. So everyone can have the computer, so they can solve for the finite element, right? So that's why this approximation method has gained much popularity, and people start to develop this field further, and now it's quite mature, and it's got a lot of the way so high that you can go along the way, and you will see a lot of the advanced technique will come in the next 20, 30 years next, right? And that the purpose of this is to make you analyze the problems easier, more accurate, and use less computing effort. This is the purpose of how people develop the method here. And there are a lot of the field that people try to do, right? And very useful. Yep. I think you may have a break now. Okay, guys, I think I talk a lot now. So any questions before we finish the class as a whole semester? Any question? No? Okay, if you don't have the problems, we're going to meet again sometimes, right? If not, so I wish you the best luck, and hope you enjoy. For those who we finish the coursework in this semester, hope you enjoy your research. You have to take the research for a year, right? And otherwise, I see you at the school next semester. Next semester, we should resume back to on-site as a full-time. And don't forget to submit the assignment. And that's all. Just do your best, enjoy your learning, and enjoy coding. Okay, that's all for me. We don't have the question, so I'm finished the class.